Hello everyone, this is the second video of chapter 21. We continue with Ádám to explore the interruptions. Let's take a look at how interrupt handling works in the microcontroller.
We can set interrupts for several peripherals of the microcontroller too, for example to a digital input, timer, ADC, or communication interfaces. Each peripheral and hardware work according to the set values in the belonging configuration registers. During their operation, they change the values of the output registers. In the simplest case, the given leg of the microcontroller works as a digital input because we set its belonging bits according to our desired operation. If we configure a digital input as an interrupt input, we can also achieve this if an interrupt event happens, when the belonging interrupt bit of the given leg, which is a bit of a hardware register, will be set to 1. The main essence is that it happens with hardware at the same time while the program runs. The datasheet of the Atmega16A contains a table called the interrupt vector table, which summarizes all the possible interrupt inputs. For example, here you can see int0, external interrupt request 0 interrupt, or int1, external interrupt request 1 interrupt input. Reading more from the datasheet, it also shows that in the case where there are multiple interrupt flags set to 1 at a given time, the handler with the smaller interrupt vector number will run first. For instance, in case of int1 and int0 pins, int0 will have priority. The Atmega16A microcontroller has a level 1 interrupt controller, meaning that the running of the interrupt handler cannot be interrupted by another handler. The interrupt flag might get set, however it can be executed only after the interrupt handler routine has completed its course.
In case of complex microcontrollers, we can set the priority of multiple interrupts. We can even set priority levels as well. In a system like this, an interrupt can only be interrupted by a higher level handler that has higher priority. However, if there are two interrupt requests at the same time, the one with the higher priority will run first. So, if a new interrupt is detected, the system then stops the execution, it runs a new interrupt, then goes back to the original interrupt. When it is finished with that, it returns to the main program. Sticking with a similarly simple example as Atmel, the PIC18F series has two user-selectable priority levels. During the configuration of the peripheral interrupt, you can assign the interrupt source to either high or low priority. This way, during the execution, the higher priority interrupt can disable the low-level interrupt. However, the ones with the same priority cannot disable each other.
Now we can see when new and different types of interrupts arrive, while the interrupt handler runs, then the corresponding flags are set. However, the occurrence of the same type of interrupt, for example int1 input, will not be registered by the hardware. So the interrupt is a very effective tool, but you have to know how to use it. But be careful, the interrupt handler name might be confusing. It is possible, although not recommended, to implement all the event handling codes in the handler. Always try to implement the bare minimum that is necessary inside the handler, such as saving some data specific to the interrupt. Button pushed, the temperature is above the critical level. Everything else should be done in the main program when we really need the result. This way, we can decrease the chance we miss another interrupt. Now let's move on to how we can set up interrupts. In order to use this function of the microcontroller, we need to enable the interrupt request of the given peripheral and the global interrupt of the microcontroller. This decision can be implemented by setting the corresponding bit of the peripheral register and setting the global interrupt enable bit to 1. Sometimes we do not want the main program to be interrupted at a certain point, for example time and/or safety critical tasks, by one or even all the peripheral interrupts. We can achieve this by setting the corresponding bits to 0. This way, the interrupts that come in during the process will only be applied after the re-enablement.
While running the interrupt routine, the controller automatically modifies some of the bits. After entry, it blocks the interrupts and deletes the flags belonging to these interrupts. At the end of the handler, it enables the interrupts again.
After getting to know the interrupts in detail, let's get back to our counter task. From now on, we will handle the buttons in interrupt mode, and we will increase or decrease the counter value in the handler. We have to complete the previously used output-input function, IOInit, by setting and enabling interrupts. This will be implemented in the following program lines. Let's see how our program works in detail. When calling the IOInit function, following the setup of the direction of the digital pins, the SBI macros are used to set the bits of the microcontroller registers to 1. The first 4 SBI instructions set up the external interrupts, the following 2 enable them, and the last one enables the global interrupts. The global enablement and disablement of interrupts can be also done by the SEI and CLI parameterless macros, which makes our program more readable. In the file main.c, you can find new types of functions called ISR, which stands for Interrupt Service Routine, and have the parameter xxx_vect. These are the interrupt handler functions that were mentioned earlier. They are only executed when an interrupt happens. Their parameters start with the name corresponding to the interrupt vector and end with the suffix _vect. These can be found in the interrupt vector table presented earlier. In our code, we increment or decrement the counter while paying attention to the limits in our interrupt handlers. Within the infinite loop of the main function, the only thing left to do is set port A to the value of the counter. This will show the value on the LEDs. Because the button is debounced with a filter capacitor, and we configure the external interrupt to detect a rising edge, nothing will happen if we push either of the buttons until we release them. Then, a 0 to 1 transition will occur on the input pin, which generates an interrupt, and the control goes to the appropriate interrupt handler. If it hasn't been clear by now, we would like to emphasize again. Interrupts are a very important element of embedded software development. The reason for this is that in microcontrollers, most peripherals are capable of generating interrupts. An interrupt cannot only come from an external pin of the controller, but it can also be generated by an internal peripheral, such as the analog-digital converter signaling that the conversion is complete, or if any communication peripheral receives a message, it can fire an interrupt to let us know. Usually, we can get information in an interrupt if a timer peripheral has expired. In a previous chapter of the curriculum, we've already talked about timers, but then we did not use interrupts. Let's have a look at an example where we utilize a timer with interrupts. We have already talked about the bouncing button problem, which we have solved with hardware, debouncing in the form of 2 filter capacitors. For the current example, let's remove them and implement debouncing software instead.
Before we do that, let's see how our interrupt program behaves without the filter capacitors. Let's load a new program that already uses interrupts. I'll do this too. And remove the filter capacitors. The program is now running, and let's see how it works. Try pressing the button first, and then releasing it slowly. You can see that the counter counts 2 at the same time, even though you only press the button once. If you keep trying, the count is now just right. But with more tries, you might see that sometimes it counts correctly, and sometimes it doesn't. You can see the same thing when counting down.
To avoid it, we do the following. In the interrupt handler of the buttons, we disable any interrupts coming from the same source and start a timer, which we have set up previously to have close to a 100 milliseconds period. When the timer expires, another interrupt handler will get called, where we re-enable the interrupts coming from the button. This causes the system to detect only the first rising edge, because the other edges that are caused by the bounce will get ignored as the interrupt is disabled. The approximate 100 milliseconds set in the timer is long enough to stop bouncing, but it's small enough to almost always detect 2 consecutive intentional button presses. Create a new source file called timer.c in which, as before, configure the timer1 peripheral with a prescaler of 8. The contents of the timer init function will be the following. Because the clock frequency of our controller is 8 MHz, the clock signal of the timer will be 1/8 of that. The timer is 16 bits, so 8 million divided by 8 divided by 65,536 equals 15.26 Hz, so our timer will overflow every 65 milliseconds. This time will be used to prevent the push buttons from bouncing. The contents of the io.c file can remain the same, as at startup we want the button interrupts to be active. In the main.c file, both external interrupt handlers have to be amended with a reset timer and the overflow interrupt enable, which is accomplished with the following lines. Furthermore, the external interrupts have to be disabled so the microcontroller won't recognize the rising edges coming from the bounce. In addition, a new interrupt handler has to be created for the timer overflow, in which we re-enable external interrupts and clear all interrupts flags that might have been set before the timer expired, and disable the interrupt of the timer. It can be seen here. Finally, we have to call timer init and io init in main, and then in the infinite loop set the LEDs by assigning the counter value to port A. Try to put the counter loop in main that keeps the controller busy and see what happens. Let's look at it now. Szabolcs, please program it.
I am already doing it, and if everything is correct,
I press the count up button. You can see that nothing has happened so far. However, after the 4 cycle had expired, our button press produced a result. The processor spent most of its time counting in the for loop, but then updated the output with the value of the counter and is now spending its time in the for loop again. So, thanks to our interrupt, the counter value can always be updated in the background, and we always save the current value.
in our example, it is not really important whether we wait for exactly 100 milliseconds or for around 65 milliseconds after each button press. So we were using the simpler counter mode as the peripheral for the timer counter. If you need to wait exactly 100 milliseconds, we have to use the timer in output compare mode. Here, the timer generates an interrupt when the counter reaches an exact pre-programmed value. It may very well be that depending on the push button itself and how fast you are pressing it, the 65 milliseconds turns out to be too short and we need to leave more time to debounce. However, by implementing any of these, we leave a greater window where the external interrupts are disabled, so we can increment or decrement the counter slower. The optimal solution is always application specific and depends on many factors, such as how long a button bounces, if there is a free timer available, or how fast impulses we need to detect, and so on.
We have now reached the goal we set at the beginning of the video, to introduce the concept of interruption and its rather important role. Through an example, we have looked at the use of external and internal interrupts, which I hope you will be able to use in the rest of this curriculum and beyond, in your hobby projects and your future studies. In Chapter 21 of the Crystal Clear Electronics curriculum, you were introduced to the concept of interruption, its basic properties, its use, and its important role. We also looked at an example of using both external and internal interrupts. We encourage you to gain your own experience of the subject and hope that the knowledge you have gained here will be of great help to you. In the following videos, We will also show you some important and exciting things about the world of embedded systems. Stay tuned for more!
You will find all the relevant information in the video description. Follow us on Facebook for the latest news, and we will see you soon in the upcoming videos.
Bye bye!
Bye!